Okay, so 11.2. So we're building off 11.1 with the normal distribution. So first we'll define a z-score. So a z-score is a statistical measure of a score's relationship. Numbers don't really have relationships, but relationships, so to speak, or distance to the mean. And it's essentially, actually it's exactly, it measures the number of standard deviations away from the mean. So the formula is x minus mu over the standard deviation, where x is whatever the score is that we're looking for. Mu is the mean. Sigma is the standard deviation. So here's how this works. Suppose a student could submit either their SAT score or their ACT score to a particular college. Their ACT score was 550, SAT, excuse me, was 550, their ACT was 24. Which score should the student submit? So we want to figure out like which one's better. And just looking at the numbers, it's like, well, I don't know what's better. And presumably this is just one section of the SAT, but we can't necessarily tell which one was better until we can kind of measure them and actually come up with a way to compare them, okay? So if we calculate our z-scores for the SAT, our z-score is, x is our score, so the score this person got was 550, minus our mean, which was 500, all over our standard deviation of 100. So that's 50 over 100, or 0.5. So that means that the SAT score was 0.5 standard deviations above the mean. For the ACT, the z-score was the score the person got, which was 24, minus our mean of 18, all over our standard deviation of 6. So this is 6 over 6, which is 1 or 1.0. And so what this means is that since these are positive z-scores, that means basically above the mean. And so this student should submit the ACT score because it's higher above the mean, or a greater distance above the mean. So the ACT score was 1 standard deviation above the mean, whereas the SAT was half a standard deviation above the mean. So now let's look at the normal distribution here and also do z-scores again. So if our mean is 50, our standard deviation is 6. Well, let's kind of draw. I always like to draw the vertical lines. It would help if I actually connected the points like I wanted to, but okay, so if our mean is 50, standard deviation of 6, we'll add 6, and then we'll subtract 6. Okay, so if we want to find the z-score of 62, z is going to be x, which is just that value, 62, minus our mean of 50, all over our standard deviation of 6. This is 12 over 6, which is 2. So what this means is that the score is 2 standard deviations above the mean. Well, look at our distribution. Here's the mean. We count 1 standard deviation, 2 standard deviations. There we go. Like magic or something, or just like math. Let's look at the z-score of 44. So z is 44 minus our mean of 50 over 6. That's negative 6 over 6, which is negative 1. So that score is 1 standard deviation below the mean because it's a negative number. And oh look, if we go 1 to the left, 1 below the mean, we get to 44. So this is 1, 2 to the right to get 62, 1 to the left to get 44. So why use z-scores? Why do we even care? Well, we use z-scores to avoid rescaling each normal curve to fit each unique mean and standard deviation. So we're standardizing the data by converting values to z-scores. And then you use a z-score table to find percentages and percentiles. So here's what we do here. So if we started with our values of just copying from up above, 32, 38, 44, 50, 56, 62, 68. Again, I'm just looking at these right here. So instead of writing it that way, we'll have the mean be 0 because it's 0 standard deviations away from the mean, and then 1 away, 2 away, 3 away, 1, 2, or 3 above, and then negative 1, negative 2, negative 3. So this is your mean, and these are 1, 2, and 3 standard deviations above the mean, and these are 1, 2, and 3 standard deviations below. Now let's talk about a percentile. So a percentile, first of all, define it. It's the percentage of people / objects that have the same score or less than your score. So less than or equal to your score. So first, let's find the z-score for an ACT score of 18. So we did this before. So as far as calculating z-scores and the ACTs, so z is going to be our 18 minus our mean, which is 18, all over our standard deviation of 6. This is 0 over 6, which is 0. So when we're dealing with z-scores, we always need basically a number and then 2 decimal places. So in this case, we'll have 0.00. Okay? And the way this works is these first 2 values, the 0.0 something point something, this gives you the row that you look at. And the last number gives you the column. So if we look at this portion of the z-score table, and I will put a full z-score table in this folder with this video and stuff, so you'll be able to use it for the homework. So now if we look, percentile for a z-score of 18 is the probability that z is less than 0, because that's our z-score, right? We got 0. Don't worry about the less than or equal to versus less than. That's kind of more complicated statistics than we're going to get into. So this table, probability that z is less than 0. So we're going to look for 0.0 in the row, so right there, and then 0 in the column. So those meet right there at 0.5000. So the probability that z is less than 0 is 0.5. Okay, so our percentile is 0.5. Or like 50th percentile, right? So now let's find the z-score for an ACT score of 22. No, let's actually do 19, okay? These are both going to be 19 instead of 22. So z is going to be 19 minus our average, which is 18, all over our standard deviation of 6. This is 1 over 6. We round to the hundredths place for these, because that's all we have in terms of the row and column is something point something and then another value. So this rounds to 0.17. So 0.1 is our row, and 7 will be our column. So let's see, 0.1 is right there. We're looking for our column that's 7, and so we'll just see where these meet. Works easier if you have paper and you can just follow with your fingers. You get 0.5675. So that means the probability that z is less than 0.17 is 0.5675. But now what we wanted to know is what percentage of test takers will score above 19. Well, if about 57% score below, basically the rest of them will score above. So probability that z is greater than 0.17 is going to be 1 minus what we just got, which is 0.4325, and it says what percentage, so we can just say 43.25%. Now we have some more information here. The data for the length of 10th grade girls' hair is normally distributed with a mean of 10 and a standard deviation of 4. Let's look at the z-score for a hair length of 11. So z would be 11 minus our mean of 10 over our standard deviation of 4. 11 minus 10 is 1. 1 over 4 is 0.25. So then if we look at that, we're looking for the percentile, so the probability that z is less than that value, 0.25. We'll go back up here. So 0.25 is going to be 0.2, and then here's our 5. Where do they meet? 0.5987. And technically, if we want to say what's the percentile, that's about the 60th percentile, or you could say the 59.87th percentile if you wanted to. Now let's suppose the z-score is negative 2.68. We want to know the percentile. So we're looking at the probability that z is less than that negative 2.68. So if you look at the z-score table that's in this folder where all this today's stuff is, it's a nice mathy word, stuff. Anyway, one page is all the positive z-scores, and the other page is the negative z-scores. So keep that in mind. So here, unfortunately, this is really quite blurry. I'll zoom in a tiny bit, but negative 2.68 is going to fall. This is negative 2.6. Notice, too, that this actually goes down. So this is 0.09, 0.08. And so they'll meet right here. And again, I don't expect you to be able to read that on my copy. Maybe yours is better. I apologize. But that equals 0.0037. And so technically, if you multiply this by 100, it's really like the 0.37th percentile.